Ice tables lecture number 20. So we're going to expand on this idea of the equilibrium constant. Instead of calculating this values to predict whether we are at equilibrium, we're going to take this idea of and apply it so we can take where we initially start and calculate concentrations at equilibrium using a process we call an ice table. So if equilibrium quantities are given, we simply substitute those values into K and calculate its value. So if we have an idea of what those concentrations are, we can calculate Kc, or our equilibrium constant, by expressing those values. But more typically, we have an idea of what the concentration or the amount of species we have at the beginning of a reaction, and we are going to then use this equilibrium constant to predict what those concentrations are going to be at the end, using this ice table or a reaction table. And these tables are always going to have a balanced chemical reaction. The I is going to stand for the initial quantities of those reactants and products. C is going to be the change where we are initially, how do we have to change those concentrations as we move towards equilibrium. And the E is the equilibrium expression, the equilibrium values. Right? So we are essentially going to set our initial concentrations and then predict what, by using a single value, predict what those concentrations are going to be at equilibrium. So for example, in a study of carbon oxidation, an evacuated vessel containing a small amount of powdered graphite is heated to 1080 K. Gaseous carbon dioxide is added at a pressure of 0.458 atmospheres and carbon monoxide forms. At equilibrium, the total pressure is 0.757 atmospheres. Calculate our equilibrium expression. Okay. Right? So we know what our initial concentration, so we're going to set up this ice table where we're taking our reaction that's occurring, carbon dioxide plus our graphite is going to form this carbon monoxide. We're going to set up our initial, this ice, or the I in the ice, is going to be the initial concentration. We're only starting with an initial concentration of carbon dioxide. The graphite, because it's a solid, we're going to ignore. So we're going to see that we're just going to ignore its amount here. Right? And at the beginning of this reaction, it's an evacuated container, so there's only the carbon dioxide we put in. So the carbon monoxide value is going to be 0. Right? So if we look at this, we have no products, so we're going to move in this direction. We're always going to form or in this case, we're going to form products. Right? So as the change that's going to occur as we move from where we start with to equilibrium is that we're going to lose some amount of carbon monoxide, and we're going to form that same amount times the stoichiometric coefficients of products. So in case for every one of the carbon dioxide we react, we form 2 carbon monoxides. So if we're losing some amount X here, we're going to form twice as much X there, so that the coefficients carry down because this X is the smallest value. So then at equilibrium, the amount of carbon dioxide is going to be the amount we started with, that initial value, the 0.458, minus the amount that was reacted. The amount of carbon monoxide that we have at the end is going to be twice that X. So the amount of carbon dioxide will decrease and the amount of carbon monoxide will increase. And that change will be equal. So we'll lose X and we'll gain 2X. Right? So if we know the values at equilibrium, we can then solve these equations and calculate K. So now we have these terms of X. We know that the total pressure at the end is going to be the pressure of the carbon dioxide and the pressure of the carbon monoxide, and we know its value. So that total pressure is going to be equal to the pressure of carbon dioxide, which we said at equilibrium is 0.458 minus X, plus the amount of carbon monoxide, which is 2X. So we're going to set this up from the table and solve for X so that we see that this change is going to be equal to 0.299 atmospheres. So then at equilibrium, our concentration is going to be this 0.458 minus X, or 0.458 minus 2.99, to give us a concentration at equilibrium of carbon dioxide of 0.159. The carbon monoxide is going to be 2X, or 2 times the 0.299, or 0.598 atmospheres. So now that we have the equilibrium amounts of those, we can solve this for this K value, where we're going to take the pressure of the CO2 squared divided by the pressure of the carbon monoxide. So that's upside down. The pressure of the carbon monoxide squared divided by the pressure of the carbon dioxide. So the 0.598 squared divided by the 0.159 gives us a Kp value of 2.5. Right? So that's one thing. We can also, if we know our equilibrium constant, we can then use that constant and some initial conditions to calculate the concentrations at equilibrium. So for example, at 1280 degrees Celsius, the equilibrium constant for this reaction, Br2 goes to 2Br, is 1.1 times 10 to the minus 3. If the initial concentrations are of carbon or bromine, Br2 is 0.063 molar, and the concentration of bromine is 0.012 molar, we can calculate the concentrations of these species at equilibrium. So we're going to set up an ice table. So it's easier to actually look at how to solve this problem this way, so we're going to look at it here. Right? So we have to set up this ice table. So we have Br2 as a gas is in equilibrium with 2Br as a gas. Right? And we need to set up an ice table. So our initial concentration of each of these species. So the initial concentration of Br2 is this 0.063 molar. The initial concentration of the 2Br is this concentration, 0.012 molar. Since, unlike the last example where we only had one of these, it was clear which direction we're going to shift, now we have concentrations of both. Right? We also know that the equilibrium constant K is going to be equal to the concentration of Br squared divided by the concentration of Br2, which is equal to 1.1 times 10 to the negative 3. So the relationship of these concentrations is going to be this value at equilibrium. But the question is, are we at equilibrium? Remember from before that to calculate whether we are at equilibrium or not, we have to compare Q to K. If we remember, the Q has the same relationship as K. This is just maybe not at equilibrium. So Q is also going to be equal to the concentration of Br squared divided by the concentration of Br2. Right? Up here, this is at equilibrium. This is some other place. So we're going to then take these concentrations, put them into here, and see what we get. So 0.012 squared divided by 0.063, and we find that we get a value of 2.28 times 10 to the negative 3. Right? So we're going to compare this value, Q, to K. Right? So if we look, Q, 2.28 times 10 to the negative 3 is larger than 1.1 times 10 to the minus 3. This is a bigger number. So Q is greater than K. Right? So if Q is greater than K, that means we have too many BRs compared to Br2 than we should at equilibrium. So with Q greater than K, we're going to shift toward our reactants, or in this direction. Right? So some of this mass has to be shifted back in this direction. Right? Which means the change that's going to occur is we're going to lose some amount of Br, which will be gained then on this side. Right? The smallest amount that we can lose is X, and for every one of these that we make, we have to react 2 of these, so this is going to be 2X. So then at equilibrium, we're going to get a concentration of 0.063 plus x and 0.012 minus 2x. Right? So these are a representation of our concentration at equilibrium, which got to be related through this. So we're going to set up our K is equal to the concentration of Br at equilibrium, 0.12 minus 2x. But this is squared divided by this concentration, 0.063 plus x. And all of this relationship has to be equal to their K value, 1.1 times 10 to the negative 3. Right? So if we do that, we're going to end up just expanding this here using our FOIL, if you remember from algebra. Right? So to simplify that, we're going to end up with 1.44 times 10 to the negative 4th, this squared, plus 2 times this, so 0.012 times 2 times 2 is going to be equal to, and it's a minus, so minus 4.8 times 10 to the negative 2, plus that squared, which is 4x squared. So that divided by 0.063 plus x is equal to 1.1 times 10 to the negative 3. Now, if we notice here, this is not going to be able to be simplified simply, right? It's going to take some work to do this, and because this is a quadratic expression, or the squared, we're going to have to use the quadratic formula. And if you don't remember the quadratic formula, it is for a quadratic equation where we have ax squared plus bx plus c is equal to 0, then x can be solved by taking a minus b plus or minus the square root of b squared minus 4ac divided by 2a. So then we have to simplify this and set it equal to 0. So we're going to combine like terms and set it equal to 0. Okay? So we need, like I said, we're going to simplify this into this form and then stick it into that equation. So we're going to end up multiplying this over, so we get x's on both sides of the equation. So we're going to end up with 1.44 times 10 to the negative 4th minus 4.8 times 10 to the minus 2 plus 4x squared is equal to 6.93 times 10 to the negative 5th plus 1.1 times 10 to the negative 3x. Right? But we want it equal to 0, so then we're going to move it in this direction. So we get 7.47 times 10 to the negative 5 minus 4.91 times 10 to the negative 2x plus 4x squared is equal to 0. Right? And then I'm just going to rearrange them so that it's in the same format. So we get 4x squared minus 4.91 times 10 to the negative 2x plus 7.47 times 10 to the negative 5 is equal to 0. Right? In which case 4 is going to be our A, 4.9 times 10 to the negative 2 is our B, and 7.47 times 10 to the negative 5 is our C. So we're just now going to stick it into this equation where x is equal to a minus B, which would make this a plus 4.91 times 10 to the negative 2, plus or minus the square root of b squared, 4.91 times 10 to the negative 2 squared, minus 4 times a, which is 4, times c, which is 7.47 times 10 to the negative 5, all over 2 times a, which is 4. Right? So when we do this, right, once with this being added, once when this being subtracted, we get x to be either equal to either 0.018 or 0.010. Which one is it? Well, remember what we're trying to solve here is for the concentrations at equilibrium. So we have to go back and calculate the concentration of Br2 and the concentration of Br. Right? From our ice table, right, we know that Br2 is going to be equal to 0.063 plus x, and Br2 is going to be 0.012 minus 2x. So if we put this one in, we'll solve for it, and then we would solve for it this one. One of them is going to give us something that doesn't make sense. Right? So if we do the first one first, we're going to get 0.063 plus 0.0018 gives us a concentration of 0.061 molar. Excuse me. If we put it in here, 0.012 minus 2 times 0.0018, we get a concentration of 0.0084 molar. If we do this again with this concentration, we see that 2 times 0.1 is 0.01 is 0.02, which is bigger than this number, so that would give us a negative value. So that is not the right number. So these two are our concentrations we're solving for. Right? It's a fairly long process. Mathematically, the chemistry itself, setting up the ice table, is fairly straightforward. After this point, all of the rest of this, unfortunately, is math.